All right, let's get the rest of 2.1 in. So let me get this screen up and we'll get going. Right, it's the audio working? Yes, okay. All right. All right, so now we have a good idea. We've done a couple truth tables. You have a good idea kind of how to play those out. So now what are some of the things that they're useful for? And also let's get to what do you call it? Again, like I said, so some of the idea of this class is both learning the logic behind these things, but then using that logic to prove things. So we're actually going to look at sort of some of the first things that we can start to prove now that we have this tool called a truth table that tells us in general, again, in abstract, the truth value of some logical statement, no matter what the actual content or context is. So one of the first things we're going to prove, one of the first patterns that we get to look at is what's called De Morgan's law. Named after mathematician. I think it was more than just a mathematician, but mathematician named De Morgan. But forget that it's a law, it's some theorem, somebody, published it somewhere. So let's forget that because none of that really matters. Again, everything that we learn in mathematics, all these theorems and everything is just some pattern that we're trying to figure out kind of the truth value of. Is it true or false? So the pattern or the idea that we want to talk about, that we want to figure out is, let's say I have an and statement. What happens to that and statement when I negate the whole statement? So we saw some examples on the previous couple truth tables where we negated one of the statements and then we combine it with another statement with an and or an or. What happens when we negate this whole statement? So the first thing we're going to do is let's figure out the truth value for a whole statement, for that whole statement. So just go through that exercise. And then what we're going to do is we're going to look at, is it equivalent? Is it the same? Is the pattern the same as maybe some other statements? Well, anyways, so we'll kind of get there. Well, let's start there. I may not even have enough time to finish, so I'm gonna have to finish this later, but so we'll make a part 3 out of this, and that's fine. But let's make a truth table for this. Now, this is only 2 statements, a P and a Q. So it looks like we can get away with 4 rows here to cover all of the possible combinations of truth values for the inputs. So we can get away with, we'll have true, true as one of our possibilities. We'll have true, false. We'll have false, true. And we will have false, false. So those are our possible inputs for P and Q. So then what we want to do is we want to create this statement, the truth values for this statement. So again, what you want to do is you want to think about kind of what actions or what operations or what statements are you going to need to create that end statement. And notice that there's really 2 operations here. There's an and between P and Q, and then you're going to negate all of that. So that's the 2 columns we're going to need to figure out here. We're going to need to do P and Q. And then we're going to need to negate that, whatever we get for P and Q. And that gives us the truth values for that final statement. So literally this reads the final statement. So you're going to need to figure out P and Q, and then not P and Q. So I actually want to give you guys the time to do that. So I'll pause, you pause. I want you, on the last one, we kind of did one column by one. I want you to go through and do both columns from here because you can do that. You have enough from the previous part of the lecture, you know exactly how to do that. So I'll pause, you pause, go ahead and fill out, figure out or kind of fill out the rest of the table, get the truth values for both the columns here and then for so yeah, yeah. So I'll pause, you pause. All right. So for P and Q, we saw this too in the last part of the lecture that so true and true makes true, but then everything else is going to be false. So an and statement is only true when both parts are true. So that's going to be false, false, false. Then we're going to do not P and Q. So here's kind of the fun part. So not P and Q, you're going to take everything in P and Q and you're just going to negate it. You're going to flip it. So that's going to then be false, true, true, true. All right. So this is not P and Q. So right now, this is not even De Morgan's law. This is just an observation. So this is the statement, not P and Q, and this is the truth values of it, depending on your inputs for P and Q. And here's where we do get De Morgan's law. So what I want us to do a couple experiments here. Sure I have enough room for this. So what De Morgan's law is about is, again, forget a theory. What he was wondering about, what he was trying to figure out is, so then not in terms of truth values, but symbolically, what happens when I negate an and statement? What do I get? In terms of the structure, the logical structure of that statement. And so we're going to experiment. Well, what's the best way at this? Best way at this is if you guys were here and I can get you to guess. So that's the first thing is you really want to try to guess. So what do you think happens when you negate an and statement? What do you get? And so hopefully it at least makes some sense to you that we talked last time how the and or are sort of complements of each other. They're not complete opposites, but they're at least complements. So maybe when you get, so the idea, the hypothesis is maybe when you negate an and statement, you get an or statement because you're kind of flipping it to its complement. And you would also figure that if you're negating the statement, you would maybe negate both of these pieces here. So the hypothesis, the idea is that maybe when I negate, so let's write it this way. When I negate P and Q, maybe I get an or statement with not P where I negate the P and I negate the Q. Now the thing is, I have no way to prove that. Like I don't know, the patterns, the properties of negation doesn't actually say that it definitely does this. This is just a hypothesis. And so how do I prove this or how do I test this out? So the way we're going to test this out is we're going to build the truth table for not P or not Q, and we're going to see if it matches. We're going to see if our end statement matches the same truth values we see there. And if they do, then what we're saying is these two statements are inherently equivalent to each other. They're inherently the same because for the same truth values for the inputs, I get the same truth values for the outputs. So what I'm saying is we're gonna build another table and we're gonna write P and Q, and we're gonna write P and Q the same way with the same inputs, same order on the inputs. So true, 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 false, false, true, and false, false. And then what you're going to do from there is you're going to build this statement. So notice for this statement, there's actually three operations. We got to not P, we got to negate P, we got to negate Q, and then we got to put an or between the two. So we got to do not P or not Q. So you're going to need a column that says not P. You're going to need a column that says not Q. And then you're going to build our ultimate statement, our actual statement, not P or not Q. So we need to work our way across this table and build the parts and build this final statement. And then again, the question is going to be, do they match? Does the truth values here match the truth values there? Because if they do, again, because we made the inputs the same combinations in the same order, what we're saying is these two statements then are inherently the same. If you put in a true and a true, you get out the same. If you put in a true and a false, you get out the same. So they're, we're going to say they're equivalent. They're logically equivalent. They're the same statement, just written a different way. So let's test this out. So same deal. I'm going to pause. You're going to pause. Go ahead and fill out the rest of this table and let's see what we get. All right, see what y'all got. So for the not P column here, it looks like that should be false, false. So we're just going to flip these. So false, false, true, true. Cool enough. And then for not Q, we're going to flip the Q column. So this is going to be false, true, false, true. And then we go to the not P or not Q. So now we're going to take these two columns and we're going to do an or. So false or false. What does that give you? Good, that gives you false. False or true. What does that give you? Good, that's true. True or false. What does that give you? That's true. And then true or true is obviously also true. Notice that again, this column, so I'll just kind of, well, so don't want to put too many lines here. So, but notice that this column exactly match each other. So if they exactly match each other, then these are completely equivalent statements. That means that not P and Q is the same as, it's completely equivalent to not P or not Q. And this we call De Morgan's law. So what De Morgan's law does is it gives you a pattern for how to negate an and statement. If I'm negating an and statement, then what I'm saying is you negate each part and you flip the and to an or. But this is the way we prove it. So the thing is, there's nothing about the negation by itself that says that that should be true. The way that you prove it is you build the truth tables and you show that the truth values for each of those two statements is exactly equal, exactly matches each other. And besides this being like your procedure, that's how you prove it. Okay, that's the thing you do. Again, you should let that blow your mind for a second. Like, they're equivalent. They're the same. So they actually mean the same thing. They say the same thing. They just read a little differently. So we could go through this again and you would see this similar thing. So if we wanted to negate P or Q, then so from here, we could prove it with a truth table, but you can probably extend the pattern there. And negating P or Q, what would you get there? Good, that should give you not P, should give you not Q, and then you should be flipping the or to an and. So not P and not Q. So this is De Morgan's laws. It's a pattern for how to negate and an or statements. And so, like I said, the amazing thing about this is that, again, we're saying like, not just that we can prove this is true, so then this is actually true. I can take an and statement and I can rewrite it this way, and it says the same thing, means the same thing. It is actually the same statement, just in English or whatever language you're using, written a little differently. So let's do that actually. So that's the The next several reading assignments that I gave you guys, that's really what that was about. So I think I gave you guys 25 and 27. Let's look at those. And I'll leave I'll leave that up there though. So let's go look at 25. Yeah. That chapter 2. So 25 says Hal is a math major and Hal's sister is a computer science major. So notice that that's a and statement. And they want you to write the negation of that statement. So we want to basically say that the opposite of that Hal is not a math major. So anyways, yeah, so we want to say the opposite of that state of existence. And so the way we're going to say that is we're just going to do exactly the pattern that we see for De Morgan's law. If I want to negate an and statement, I change it to or, and I negate each part. So what I'm going to say here is Hal is not a math major. Or, sorry, Hal's sister is not a computer science major. And that would be the negation. So all you do is do exactly what we did symbolically, but now you're just doing it in words. Change and to or, say the negation, say the opposite of each of those statements. So, and this works. So again, notice that if the original statement, let's say the original statement was true, Hal's a math major and Hal's sister is a computer science major. That means both that Hal's a math major and Hal's sister is a computer science major. So then the negation of that would be something false. To be false, we see for and statements to be false, one or the other just has to be false, just has to be not true. And that's what our negation says. Either Hal is not a math major or Hal's sister is not a computer science major. So it follows logically that that has to be the negation of it. That's the only way we could negate it. I made a big deal about I think this book being kind of funny. So if you're not getting the hidden joke here, in what do you call it? Arthur C. Clarke's 2001 is was it? Is it 2000? Yeah, 2001 Space Odyssey. Hal is the computer, the AI computer on their spaceship that ends up basically kind of killing the humans. So because what they were asking to do was not logical. And so her naming this person Hal is actually to me pretty hilarious. Not a math major and his sister not being a science major. So there's a nice little Easter egg, a nice little callback there. That's pretty cool that she did. So and then I also give you guys 27. So you were negating an and statement there. 27 is an or statement. The connector is loose or the machine is unplugged. And so I actually want to ask again, I won't be able to hear, but I want to just give you a second to pause to look at. So how did you write the negation of that? Good. When we negate an or statement, we change it to an and we negate each part. One of the things I want to focus on here on the first one, 25, you were kind of looking at, you're either a math major or not, right? Or you're the computer science major or not. when we negate on 27, there's kind of a question of what is the negation, for instance, of the connector being loose? So in order to logically analyze things, we need these statements that have a binary conditions or setups. So on or off, basically. So what's the on or off for loose? What's the negation of loose? But it should be tight. So just so a couple things about 27 that usually comes up when I have a class in front of me or on Zoom and I actually have some interaction. There's a couple different ways you can say this negation. You could just say the connector is not loose. I would allow here also saying the connector is tight, basically. Because in terms of, again, if you're doing some construction or you're an electrician or a plumber or whatever, things are either loose or they're tight, right? Loose, yeah, they're either tight or they're something less than tight, which is loose. There's some give there. However, there's a good argument to be made of like loose and tight are not like, I mean, it's sort of colloquial, right? It's not this definite on off, or this condition or that condition, right? Because to be loose is a whole range of conditions. So if you don't feel, so I've seen some students that they don't feel comfortable saying, what do you call it? Sorry. They don't feel comfortable saying tight and loose because loose is a bunch of conditions. So they'll just say it is not loose, right? Or it is not tight or something like that. That's a perfectly fine way to negate it. But what I'm saying for the rest of you guys is I'll allow that idea that when I'm looking at this sentence and I'm looking at a connector, something that you're screwing in, either being loose, then the opposite of that is pretty clearly tight. There sort of isn't this gray area between there. You're either, your washer, your pipes that you're screwing into each other, whatever context we're looking at, they're either loose or tight. So I'm gonna say here, the connector is tight. And so where you could change or to and the machine. So this is again another one. You could say it's not unplugged, but in terms of when you plug something in, something is either plugged in or not, right? So that's hopefully in your mind kind of a clear binary thing. It's either plugged or not plugged in. So the negation of unplugged is plugged. So and the machine is plugged. Good. All right. What I'm gonna do is I need to eat lunch before my class starts. I have classes starts in about 20 minutes. So let me try to eat some lunch really quick. So there'll be a third part to make up this lecture. We actually don't have much to go over. I just need to eat. Well, actually, give me a second. Maybe I don't need to eat. Maybe I can just do this really quick. Um, This other question. I could do over. Look at what I have left. Maybe I need to. All right, well, let's just try to do this bit quick. Hopefully I can finish this in like 5 minutes. All right, good. So that's De Morgan's law. So this is, notice again, this is a pattern for negating. So now that we know negation exists, or it's a structure for these logical statements, we're gonna start to figure out patterns with it. So there's actually a lot of other patterns with logical statements, and I definitely don't want to go through proving all of them. I actually love going through proving all of them, but it would take way too much time. But let me just mention some of these other patterns though. So she mentions them in this section. I think she redoubles this in kind of 2.4 when we get there. But some of the other patterns that you're gonna see, I mentioned one of them earlier, but if I have something like P and Q and R, that is equivalent. I can rewrite that as P and Q and R. So I can change the parentheses, I can change the order that I do the operation in, as long as I have the same operations all the way through and I get the same result. And this is also true with the OR symbol. So if I do P or Q or R, that's equivalent to, it's exactly the same as P or Q or R. And I want you to notice something about these patterns. I want you to notice that these patterns are actually the same idea that we have from just arithmetic. So for instance, if I have 5 plus 4 plus 3, so if I do 5 plus 4 and then add 3 to it, is that the same? Do I get the same result if I do 5 plus 4 plus 3? That I do. We know that for both, not just addition, but we know that also for multiplication. So if I do 5 times 4 and then I multiply that by 3, I get the same result as if I do 5 times 4 times 3. So this same pattern of I have the same operation all the way through and I can switch the parentheses. This same pattern showed up in algebra, and the name for this pattern in algebra was the associative property. And it's the same name here. So the and the or operators have the same pattern, the same property as multiplication and addition do in algebra, the associative property. And so it ends up that actually a lot of the same properties that you have in algebra for addition and multiplication specifically, you end up having those same patterns with logical statements using your and your or operators. So for instance, you also have the commutative property. So P and Q is equivalent to Q and P. So I can switch the order of the statements, the numbers I'm using, but here they're statements, and I get the same results. Same thing for the or operator. Sorry, let's make that a Q. And we called that the commutative property. So we called that the commutative property in an algebra class, and so we call it the commutative property in this class as well. There's a commutative property for the and the or operators in, what do you call it, in logical statements. So like I said, so the curious thing here and the fun thing, if we really have the time, is you can go through not all, but a lot of the properties that you see in algebra, a lot of the patterns that you see in algebra with multiplication and addition, you end up getting the same results. You have the same patterns with and or. And that should make you, again, that should blow your mind. You shouldn't just kind of be like, oh, okay, whatever, like walk away from that. Like, that's kind of incredible. So what we're saying is now we're saying that the way multiplication and addition works with numbers somehow and for some reason has the same patterns as and or operators with logical statements. Why? What does that mean? What does that imply? Again, about the universe, about construction of things. That's kind of crazy. Because multiplication ultimately has nothing, it's not the same as an and. Addition's not the same as an or. Like they really have no contextual, like you can't even map one to the other and be like, oh, they sort of relate to each other in some way. They don't. They're completely different operators and completely different with completely different objects in different contexts that have nothing to do with each other, and yet they have the same patterns. So that's weird, and that should freak you out and get you to think about some philosophy and cosmology and stuff like that. But they do. So I want to mention that she actually makes a list of these properties that are the same. So let me see, I may actually point you to that or just tell you where it is. So I'm pretty sure. Yeah, so at the end of 2.1, you guys would have read it. There's a summary of logical equivalences, and she gives all these properties. There's distributive laws. So distribution works kind of the same. Actually, it works the same with addition and with and or as it does with addition and multiplication. So that actually works the same. There are some other laws, double negative laws, negation laws that work the same as essentially a negative does in mathematics and with numbers. So take a look at the end of 2.1. If you already read it, but take a look back at it again and look at those patterns and just think about the same, just connect them. Think about those same patterns with multiplication and addition. Because and then the negation essentially corresponds to a negative. But just think through that and make those kind of make those connections, because what we're saying is that they're the same. What we're saying is, well, you'll see in 2.4, we call so any objects with operators, with two operators, but any objects with two operators that have these same properties that she gives at the end of 2.1, we call that a Boolean algebra. So we're basically saying it acts like an algebra. It acts like numbers do with multiplication and addition. And so logical statements with and or do, but that's not the only thing. There are other Boolean algebras. So again, other objects with different operators that have nothing to do with logical statements or numbers and multiplication and addition that actually have the same properties. And again, that should make you think, what in the hell is going on? That's weird. Why would such disparate things that actually have no relationship to each other have the same patterns? Okay. So now I have 10 minutes. I'm definitely not going to get lunch. So let's finish out the last couple problems I want you to see. So those are the last couple problems for the reading, but the last couple problems that I want you to see out of this section really quick. All right. So out of this section, really quick, let's just look at I gave you guys for the homework, I gave you 30. Sure, let's look at something like let's look at something like 32, and then we'll look at 36 as well. And 32 and 36, they're saying use De Morgan's law to write the negation of this statement. And in 32 and 36, they give you something that's a little, something you've seen in mathematics before. So 32 says -2 is less than x is less than 7. So we kind of have this this way that we're used to seeing inequalities when we're saying, so what we're trying to say here is x is any number between -2 and 7, but not including -2 and 7. And we want to write the negation of this. So the key here then is if they're asking you to write the negation, what they're saying is whatever you're reading is essentially it's an and or an or statement, and you want to negate that statement. So first thing you gotta figure out is the way that you've read and thought about this. You just need to go back to the way you've read and thought about this in an algebra class. Is that an and or an or statement? So we're saying that x is some number that is both greater than -2 and less than 7. So that both, that means this is an and statement. So essentially what this statement says is x is greater than -2 and it's less than 7. So you don't have to write out this next part, but I just want to make that point that essentially what we're doing is we have this statement, x is greater than -2 and x is less than 7. That's an and statement, and we want to write the negation of that. So we need to negate the x is greater than -2. We need to negate the and we need to negate the x is less than 7. So first of all, let's talk about the x is greater than -2. What's the negation of that? So if you think about this on a number line, for instance, let's say that's my 0. Let's say this is -2. So when I say x is greater than -2, I'm saying anything to the right of larger than -2. So then what would be the opposites of that? What would be the complement of that? The opposite of that would be anything less than -2, but also -2 being equal to -2 counts, because the numbers I'm looking at here are strictly greater than -2. It's not including -2. So literally the negation of it is just everything on the other side. It's everything it's not. So it's going to be -2 and everything less than that. So the negation here is x is less than or equal to -2. And the negation of and is or. And then for x is less than 7, I think you get the idea from here, but if this is 0 and that's 7, x is less than 7 is everything left of 7. So the negation is going to be everything right of 7, but also including 7. So it's going to be x is greater than or equal to 7. And that would be the negation on 32. And hopefully you kind of get the idea from there. So on 36, we have, now what I really want to do is, that's okay. Actually, so let's do 35 instead, not 36. Let's do 35. So 35, we have x is less than or equal to -1, or x is greater than 1. We want to negate that. So in some sense, you can see part of this is going to be exactly the reverse of what we just did. We're starting with an or statement. So the first off, when you negate it, you're going to get an and statement. And when we can negate x is less than or equal to -1, then you don't have to draw the picture, but if it helps, do it. Don't consider this like elementary or something like this. Half of mathematics is geometry. Half of mathematics is proving things purely from a picture without numbers at all. So pictures is legit mathematics, or a legit tool for you to help you figure out mathematics. So let's say that's -1. So x is less than or equal to -1 is everything to the left of -1, but also including -1. So then the negation of that is everything to the right of -1, but it can't include -1 because this already includes -1. So my negation is going to be everything greater than -1. So x is greater than -1. And what's the negation of x greater than 1 going to be? That's going to be x is less than or equal to 1. And technically this is good, but then we can collapse those together like we did, like the beginning of how 32 was written, more because that's typically the way that we write it. So again, when we say this, when we say something like this, we mean and. So this is fine. Logically, this is correct, but we can collapse that. We can say that -1 is less than x, which is less than or equal to 1. And that is the negation of the original statement. And that'll get you guys through not only all the homework, but really all the concepts and ideas out of this section. So good, so it's only 2 parts. So I will post this, you guys will have both parts to go through for the homework for 2.1, and I will get to 2.2 either tonight or tomorrow. But I'll get that up for you guys. All right, see you guys next time.